Hello, we are object-oriented optometrists. That is Paul, Diageo, Resuna, and Musa. Today we're presenting our mini project, MediGraph. Diabetic retinopathy is a leading cause of blindness in South Africa. The problem? Manual screening of retinal images is slow, subjective, and requires specialists, which are scarce in many areas. Early detection is critical, but we need tools that can give a quick, reliable second opinion. Our solution models the blood vessel network of a retinal image as a graph. Vessel junctions become nodes, and vessel segments become edges. Once we have that graph, we perform two graph-based tasks. First, similarity detection. We use a method called graphlet degree distribution, or GDD, to create a structural fingerprint of the vessel network. Then we compare two images and get a similarity score. Second, classification. When using the same GDD fingerprint, we train a k-nearest neighbor classifier on images we already know are healthy or unhealthy. When you give us a new retinal image, the system classifies it as healthy or unhealthy. It's designed to help clinicians in under-resourced areas get an instant automated assessment.
Good day, my name is Paul Oluwashona, and I'll be presenting the image processing side of the MediGraph system. The image processing has four stages. First, the image is prepared to make vessels easier to detect. The image is converted to grayscale, and a smoothing filter is applied to reduce noise. A circular mask removes the black background outside the retina, and the image is converted into a binary image, where the vessels are white and the background is black. The second stage is skeletonization, where the binary vessel image is reduced to a 1 pixel wide skeleton. This keeps the structure of vessels but removes thickness, making graph extraction easier. The third stage is node detection and merging. The algorithm scans the skeleton to find endpoints and bifurcations. Nearby nodes are then clustered together to remove duplicates and noise. The fourth stage is graph construction and edge tracing. From each node, the algorithm traces along vessel parts pixel by pixel. When another node is reached, an edge is created between them. The edge weight represents the length of the vessel segment. And finally, the cleanup. Any isolated nodes with no real connections are removed. And finally, we have a clean graph of the retinal vessel network.
Hello, my name is Rasuna Mabasa. Starting with the graph implementation, we used a custom adjacency list structure, where each vertex maps to a list of its incident edges. This was implemented using our custom ADTs, where myMap maps each vertex to a myList of edge objects. We used a myArrayList for storing edges and myHashMap for fast vertex lookup. In terms of why custom ADTs were used, we avoided using Java's built-in collections and instead used our own ADTs taught to us over the duration of our course. This ensures we stuck by the assignment requirements and gives us full control over how the data structure behaves. In terms of the graph type, the graph is an undirected, weighted graph implemented using an adjacency list. Each edge is stored in both vertices adjacency lists, allowing bidirectional traversal. And finally, in terms of key design features, vertex lookup is efficient using a hash map, and neighbor access is done through direct adjacency traversal. We also handle edge duplication in the edges method. Overall, the graph supports full CRUD operations, creating, reading, updating, and deleting vertices and edges. That will be all. Thank you.
Now, let's talk about similarity detection. We use GDD. Here's the idea. A graphlet is a tiny pattern, like a three-node chain or triangle. For every node in our vessel graph, we count how many times it touches each graphlet. That gives a local fingerprint of the vessel structure. We add up these counts across the whole graph. The result is a three-number feature vector that describes the overall topology. And why is this powerful exactly? Because when a patient's condition changes, be it more vessel tuticity, fewer branches, the fingerprint changes, and GDD captures that change. To compare two images, we compute their GDD vectors and then use cosine similarity. It gives a score from 0 to 100. If it's a high score, then it means that the networks are very similar. A low score, something has changed.
For classification, we use the k-nearest neighbors algorithm to predict whether a retinal image is healthy or diseased based on its vessel structure. The idea is simple. Instead of training a complex model, we compare a new image to previously labeled images and see which ones it is most similar to. We first build a training set using retinal images that are already labeled as healthy or diseased. And for each image, we convert it into a graph and extract a feature vector using GDD. Internally, we compute the distance between the new image and every training sample, sort them, and then pick the closest case samples. The output of this is the health assessment and the skeletonized vessel map. Over here, we can either exit or start screening. So if we decide to start screening, we will be taken to our dashboard, our retinal vessel screening dashboard, and a button to take us back to the home page if needs be. We have an image preview section where we can see the original image and the skeletonized vessel structure image, and now a screening dashboard where we have the buttons in which we use to complete actions, and the results section where we can see the result of the screening. So now the first thing that we should do, or the user should do, is to load the reference images. So once we select load references, we get an extraction, and once they are completed, we have a status of the reference images were loaded successfully. After that, we can choose an image that we would want to test. The image now shows over there, and we have the image that was selected and that the image is selected, and we can run the screening when ready. Once we select run screening, we get a result. First of all, we get a skeletonized vessel structure image over here, and we get the result that the healthy pattern is detected. We then get short explanations of why we got this result. And now if the user does not understand, all they would have to do is to select this little question mark, and they will be shown what exactly it does. Let's say we would like to add this image 01_test, to the healthy dataset training images. All they have to do is press the add to healthy. We see that the image is added to the healthy dataset, and we can reload the references before screening again. So to check that, we can go to the healthy folder, and we can see now that 01_test is now there. Just for extra showing, we only have training images over here in the diseased folder. If we choose an image and it is diseased, so let's say we run and it is diseased pattern, we can add this to the diseased folder, and we will see that the test has now appeared in the diseased training dataset folder. So now let's say that the image that we chose was incorrect and we need to cancel this image. All the user has to do is click cancel image and the image is gone. And that is it for our UI. Thank you.